We'll now start to look at some of the basic matrix operations. But before we do that, let's look at a little bit of notation. First, matrices are typically denoted by capital letters like capital A, B, C, etc. And as a reminder, if I have m rows and n columns, then the size is m by n. A vector is a matrix with only one column. And vectors are denoted by lowercase letters with these little arrows over them, A, B, C, or as a bold lowercase letter, such as a boldface A. Since we can't draw boldface very well, we'll go ahead and use the arrow notation. It is common to denote a matrix in terms of its column vectors, so I may call a matrix A the vector A1, the vector A2, etc., where each one of those is just the column of that matrix. And as a reminder, the entry in a matrix that's in row I and column J is denoted by lowercase I sub j. So we always do the row first and then the column. So now that we've done my notation, let's look at actually adding and subtracting matrices. We'll start by assuming that A and B are two m by n matrices. So they do need to be of the same size. Then we can say that A plus or minus B is equal to A sub ij plus or minus B sub ij. So this is our shorthand notation that says if we want to add two matrices, we just add things that are in corresponding entries. If we want to subtract two matrices, we subtract things that are in corresponding entries. It's also important to note that our two matrices do need to be of the same size. If we have two matrices that are two different sizes, we cannot add and subtract them. So let's look at some examples of this. So here I have two matrices A and B. They both have 2 rows and 3 columns, so they're both 2 by 3 matrices. And I want to add them, A plus B. And in order to do this, like I said, we just add things that are in the same positions. So my first entry would be -5 plus -8. First row, second column would be -9 plus 3. First row, third column is 9 plus 0. I then move down to the second row. Second row, first column is -2 plus -3. Second row, second column would be -6 plus 5. And then finally, second row, third column is -9 plus 8. Now that we have that, it's just a matter of simplifying. -5 plus -8 is -13. -9 plus 3 is -6. 9 plus 0 is 9. Moving to my second row, -2 plus -3 is -5. -6 plus 5 is -1. And -9 plus 8 is -1. So I've now added my two matrices. This time I want to subtract A minus B. So in order to do that, once again, I subtract entries that are in corresponding positions. So let's start with the first row. The first row, first column would be -5 minus -8. Second column is then -9 minus 3. And the third column would be 9 minus 0. We can now move down to the second row. I would have -2 minus -3. -6 minus 5. And finally, -9 minus 8. From there, we just need to start simplifying. 5 minus -8 is 3. -9 minus 3 is -12. 9 minus 0 is 9. We can then move down to the second row. -2 minus -3 is 1. -6 minus 5 is -11. And then -9 minus 8 is -17. So now I have A minus B. Now that I've discussed how to add and subtract matrices, I want to start to look at some of the properties of addition and subtraction for matrices. One of the most basic properties of our addition of real numbers is the additive identity, this idea that A plus 0 is equal to A for any real number A. So first, I want to be able to extend this idea to matrices, this idea of adding 0. The zero matrix is going to be a matrix that contains all zero entries. So it can be whatever size we need it to be for our particular problem, but every single entry in that matrix is a zero. And we denote it by just a zero. Now that we have the idea of the zero matrix, let's look at some of the basic properties of matrix addition. I'm going to start by letting A, B, and C be matrices of the same size. So we can actually add and subtract these three matrices. They all do have the same size. My first property says that A plus B is equal to B plus A. So the commutativity property for matrices. My next property is associativity of matrices. A plus B plus C is the same thing as A plus B plus C. And then the third property, A plus 0 is equal to A. So A plus that 0 matrix behaves exactly the way we want it to. I'm now actually going to prove the first of these, the commutativity property. And I encourage you to try to do the rest of them. It's going to follow from the same basic format of the proof, and so I do encourage you to try to prove the second two on your own. So I want to prove that A plus B is equal to B plus A. I start with two matrices, A and B, that I'm going to assume are M by N matrices, so they are the same size. By definition of matrix addition, I know that A plus B sub ij, so the entry in row I and column j of the sum, is equal to little a sub ij plus little b sub ij. So this is my shorthand notation that says the entry in row I and column j came from adding the two entries in row I and column j from A and B. Since this a sub ij and b sub ij are real numbers, we know we have commutativity of real numbers. So I know a sub ij plus b sub ij is equal to b sub ij plus a sub ij. However, we can say that b sub ij plus a sub ij is equal to b plus a sub ij. So this is how we get the entry in row I column j of b plus a. And since all of these are equal, we have that a plus b is equal to b plus a. I've essentially shown that every entry in a plus b is equal to the corresponding entry in b plus a, which means these two are the same.